Let me go ahead and write these up here. This would be configuration of bismuth 3. This would be the configuration of bismuth 5. Which one of those has an octet? 5. Because on bismuth 3, the outer level's level 6, and there's only 2 electrons there. But on the bismuth 5, the outer level's level 5, and inside that xenon abbreviation is a 5th level octet. All right? So bismuth 5, the higher of your charges is the more stable one, because that's the one that has the octet.
What would happen with like element 57 if you were bringing it down? Because it's going to lose electrons too. Do you just take out that D1?
Yeah. So your possible charges there are 2 and 3.
Okay.
And we got one like that over here. Uranium's going to be kind of like that.
Okay.
This is uranium. What would be the first thing to go? Level 7. And that's 2 electrons because that's valence. And it would be all gone together. So that would make the uranium as a +2. This would be the configuration of uranium 2. What would be the next thing to look at? 6D. Is that symmetrical? Full, half full? No. And so that can go as well. So this would be the next thing you got. That would convert your uranium 2 to a uranium 3. And then we look at this. Is that full or half full? No. And so we can start removing from there. Now here's what you want to watch for though. Now we remove them individually. It's not an all or nothing thing for D's and F's. So the next thing would be uranium 4, which looks like this. And then there would be uranium 5, which looks like this. And then there would be uranium 6, which looks like this. And then you're done.
I thought that we can just remove from sub-levels S and P, but also we can do these modifications with D and F.
Yes, but what you have, you've got a different pattern to it. Because when you're removing from S and P, you empty out the entire sublevel simultaneously. If you've got 3 electrons in the P sublevel, you dump them all together. But if you've got, like in this case, 3 electrons that are in D and F, we can pluck them out one at a time. It's not an immediate simultaneous thing.
Okay.
And so that's why going from 3 to 4 to 5 to 6, we're plucking those F electrons out one at a time. All of those charges exist for uranium. Do you see how this is working? Questions about the pattern? Yes.
Besides uranium 6, what would be the most stable?
Other than uranium 6?
That one would be the most stable, correct?
Yeah, 6 is the most stable.
Or would none of them be stable?
I've seen a lot of uranium 3 compounds, so that would be my guess.
But it's going to want to lose until it becomes stable, correct?
Correct. And technically, I guess by the time you get to here, you've technically got an octet in here,
Right.
but this is not symmetrical. And so by the time you get down here, you've got the octet and the F is symmetrical, meaning empty across the board. And so, yeah, 6 is you should always go with the highest charge being the most stable one, because there's a reason it's the end of the line. Okay, it's willing to lose up to that point, but then no more. So always go with the highest charge being the most stable charge. Do you see the pattern about pulling out valence versus pulling out non-valence? All right. What do we got left over there? Iron. This is neutral iron. Predict the charges for iron. And this is what you should get. When you're looking at removing, you go to valence first. Both of those would go. That would convert iron to argon core, 3d6. And then you start looking at that D. This is your D sublevel. You've got 6 electrons in here. That is not identical across the board, across all those orbitals. So it will lose 1 to make the +3. That then becomes symmetrical across all the orbitals, and that's the end of the line. To lose 1 more to become a +4 would be busting up that symmetry, correct? And that ain't going to happen. So +3 is the end of the line. Go ahead.
Is there any other way to figure out the symmetry other than drawing it out? Or is that helpful?
Well, I mean, if you know that D sublevel fills at 10 electrons, then you know that 5 is half of that. And so when you see that you've got it to D5, then you would know to stop. If you know that your capacities are D fills at 10, F fills at 14, then knowing that half of that would be 5 and 7 respectively tells you when to stop. And then you wouldn't have to sketch it out. Question? All right. Next thing then is this page. It's a half-page grid called quantum numbers. Turn to that page. Quantum numbers is a different angle on electron configuration, where with electron configuration we were looking at position. Energy level, sublevel, orbital, whether the electron was alone or paired up, that's what's going to happen in quantum numbers. Configuration dealt with most of that, but it was really just an inventory system to tell you where the electrons are. Quantum numbers tries to go a little further based on the idea, let's say this is the nucleus. If you've got these different energy levels out here, and electrons at different distances from the nucleus and therefore different energies from the nucleus, then if you know the position of that electron with respect to the positive nucleus, you ought to be able to calculate its energy. If you know its position, level, sublevel, orbital, whether it's alone or paired up, you ought to be able to calculate the energy it has. And so quantum numbers are variables that you would plug into an equation to calculate the energy of any given electron in the atom. Now, we're going to look at the pattern for the periodic table how to determine what the quantum numbers are for the different elements, but we're not going to do those kinds of energy calculations for two reasons. One, the math is way beyond calculus. All right? That would be hard. And second, it only works for hydrogen. And there's an awful lot of atoms bigger than hydrogen that it doesn't work. Well, you know, they've only been working on it 90 years. All right, it's a work in progress. Maybe eventually they'll get it to work for other things. But right now, honestly, it only works for hydrogen. Because with hydrogen, there's one electron, you don't have to deal with repulsions and things like that. When you get up to bigger things like helium, now you got to deal with repulsions, and that's harder for them to account for mathematically. They're only mathematicians. What can you say? They wish they were chemists. What we're looking at, information-wise, is a lot like configuration. Energy level, sublevel, orbital. And the last one is called spin, but really you're looking at that orbital where 2 electrons is the maximum capacity, and you're trying to see for the very last electron you put in, is it alone in that orbital or is it sharing space with another electron? Within that orbital, does it have its very own private orbital or is it paired up with another? So, symbolically, you'll see lowercase n for level, cursive L for sublevel, M for both orbital and spin, but orbital is an M with an L subscript and spin is M with an S subscript. So level, sublevel, orbital, and spin. And we're going to do these in parts. Level and sublevel being the easy part, because that we've already dealt with. That comes directly out of electron configuration. So if we were doing quantum numbers for carbon and chlorine, then the system goes like this. Carbon has 6 electrons. We know that from the periodic table. We don't care about the first 5. All we care about is the very last one, meaning the 6th one. And judging by where carbon is on the periodic table, that last electron is in the 2nd row of the P block and 2nd column. P block, 2nd row, 2nd column. Its configuration would end as 2p2. Chlorine's configuration ends as what? Three P 5. All right. Now, this is level and this is sublevel, correct? So level is 2 and sublevel is P. Except that quantum numbers have to be numbers and P is not a number, it's a letter. And you got to have something numerical that you can plug in there. Because remember, these are supposed to be numbers you plug into variables to be able to calculate energy. So we have to have number equivalents for those sub-level vectors. And the pattern is this. For S, P, D, and F, 0, 1, 2, and 3 are the values. And so since carbon ends at the P sublevel, L is 1. No option. L equals 1 means you're talking about a P sublevel, always. SPDF is L values of 0, 1, 2, 3. For chlorine, what's N?
3.
And what's L? 1. 3 means 3, and P means 1. Those two quantum numbers come directly out of your configuration. So go ahead and fill out the rest of this chart down through CF, California. I'll put a couple more here on the board from that list, but go ahead and do all of these. last two rows on the chart, it'll be working back the other way. But going down through California, this is what you should be getting for iron, sodium, and California. Is that what you got? If not, please ask. Energy level is the easy one because that's directly out of configuration, and the sublevel is basically just a conversion from that. That chart that's up on the top right over there will convert your sublevel letters into sublevel numbers. SPDF is 0 to 0. Question on N or L. You're getting those off the periodic table for any given element. All right. Now the other two, you can get them off the periodic table, and there's a document on D2L where it shows you how to do that. But that's kind of awkward. The best way to do it and the safest way to do it is to sketch out your sublevel. For carbon, 2P2, we're dealing with a P sublevel, and a P sublevel is always 3 orbitals, correct? Always. So here's my 3 orbitals. A D sublevel would be 5 orbitals, an F sublevel would be 7. For carbon, it's a P, and here's orbital, orbital, orbital. Those orbitals are given numbers for names with the center 1 always being 0. These are odd numbers, so there has to be a center 1. The center 1 is always named 0, and you count off in number line fashion from there. Negative toward positive. And then what you do is you start putting in these electrons and see where the last one falls. And remember, when you're putting electrons in here, you make one lap through, putting them in individually, spreading them out as much as you can to reduce repulsion. And then if necessary, you go back and make a second lap, or you put them in pairs. So here's the first, here's the second. That's the one we care about. It happens to fall in the 0 orbital. So the orbital number for carbon is 0. You're keying in on that last electron and what orbital it lands in. Now the spin number, if that last electron is alone in its orbital, you give it negative 1/2 value. If it is paired in the orbital, you give it positive 1/2 value. And so here's our last electron in its orbital. It's by itself, correct? Therefore, negative 1/2 spin. Okay? That one's kind of arbitrary based on whether it's alone or paired up. This one is alone, therefore negative 1/2. Chlorine, we're dealing with 3p5. Here's the P sublevel. 5 electrons to place in that sublevel. Here's 1, here's 2, here's 3, here's 4, here's 5. Which orbital is that? 0. Is it by itself or sharing space? Sharing space, so positive 1/2. Iron, we're dealing with a D sublevel. Here's our 5 orbitals for that D sublevel. Here's the names for those orbitals. And there's 6 electrons to be placed. So 1, 2, 3, 4, 5, 6. The last electron is in the negative 2 orbital, and it's paired up with another electron. sodium, we're dealing with an S sublevel. That means there's one orbital, and the middle one is 0, right? So that's it. One electron to be placed. Here's the 1. Orbital number is 0. Spin number is -1/2. Californium. We're dealing with an F sublevel. How many orbitals in an F sublevel? 7. Center one is called 0. Nine electrons to place. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The last one falls in the -2 orbital, and it's paired up. Sketching it out is the best way to go, because it'll show you where that last electron lands. The key to doing that properly is knowing how many little lines to make, because that's your number of orbitals. S's are always 1, P is a group of 3, D is a group of 5, F is a group of 7. And then you just check in the electrons and see where they land. Question about this. Go ahead and do the other ones that are on your chart. Fill in the rest of your chart. Now, one note of warning here about doing the spin part. In the book, they have this spin thing reversed. They tell you that alone is +1/2 and paired is -1/2. Okay, I'm right, they're wrong. Don't read that, all right? Alone is supposed to be negative, paired is supposed to be positive. And I'm not just saying that because I'm egotistical, I'm saying that because there's a pattern to it. If you've noticed with the other quantum numbers, N started with 0 when you went to higher numbers, right? Well, no, actually started with 1 and went to higher numbers. L started with 0 and went to higher numbers. You always start low and go high. And when we were doing the orbitals, we started low and went higher, correct? All the quantum numbers are supposed to go from low number to high number. And -1/2 is lower than +1/2. All right? So it should be negative first for alone, positive for paired. Your book is the first one I've ever seen that had it switched, and I'm not sure why they did that. But ignore it all the same. Right? Alone should be negative, and paired should be positive. Just be aware of that if you're looking through the book. All right, at the bottom of the chart, we've got two where the sets of quantum numbers are given, and you're asked to work backwards and identify who the element would be. This being the first set. You've got 111 elements on the periodic table, at least the periodic table on the wall. And this is the set of quantum numbers for one of them. No two elements will have the same set. And so what we need to do here is break this down and identify who this set represents. And the key, like we did before, is treat these two separate from those two. Level and sublevel 5 means energy level 5, and L of 0 means S, correct? So we're talking about somebody in the 5th row of the S block. And if you go to the periodic table to see who that is, that's rubidium or strontium, correct? 5th row of the S block is just those two elements. So with N and L, we've narrowed it down from 111 possibilities to 2. It has to be one of those, because that's your 5S set. And then for this part, we're looking at it to see whether we're talking about the first electron or the second electron. Here's our S sublevel. It's just a single orbital. 0 is its name. Here's the first electron. That would be the negative 1/2 spin. And here's the second one. That's the one with the positive 1/2 spin. So it's the second electron in that orbital that comes up to be positive 1/2. And so it would have to be strong. You see how that works? Do the other one then. 3, 2, minus 1, minus 1/2. What does this information give you? 3D. And so that narrows it down to be scandium through zinc. Because that's the 3D section of the periodic table, correct? Question about that part. All right. And the other part is a little bit more awkward, but this is, now that we know that we're dealing with a D sublevel, and that D sublevel is 5 orbitals. Here's the 0, minus 1, plus 1, minus 2, plus 2. We're going to put electrons into the orbitals until we get one that's in the minus 1 orbital and alone. Is it that one? Is it this one?
Yeah.
How many electrons did that take? 2. So it's the second column over in that 3D series, which would be titanium. Second column. What that's telling us here, this 2 here, is we're talking about 3D2. Second electron into that 3D sublevel is the one we're talking about. Go ahead.
Can you write down again how many spaces there are for each row?
Well, S is always 1. P is 3. It's all odd numbers, is the pattern. So it goes 1, 3, 5, 7. It's always odd numbers. question about going from that to identifying this as titanium? If there is, please. Let's try one more, just to be sure. What does this tell you?
It's 4D.
4D. And so right now we know it's somebody from yttrium through cadmium. Got to be one of them, correct? And then we go to these and we sketch out our D sublevel.